I'd now like to welcome to the stage our final presenter for this session, Lars Skaarup Jensen, R&D Specialist and Project Manager for FLFlex Cement. So please welcome Lars to the stage. Thank you.
Thank you, David. And now I'll try to dive a little bit more into detail with developing new technologies. Paul and Antonio, they gave a broader picture of how everything fits together. And in there, I'm glad to see there's a lot of need for innovation. So this is what I particularly want to look into in my presentation. Are my slides available? There. Sorry. So this, my first slide, is a picture from Mannok Cement. And I've been working very closely with Mannok Cement for the past 6 years, developing and implementing our FUELFLEX Pyrolyzer. We've chosen this case as an illustrative case of transitioning to green because this case includes developing new technologies and processes. It also includes integrating it to an existing process, and then it also includes optimizing the overall installation to get the maximal benefits out of it. Now, as I mentioned, I'm really happy that there's a lot of need for innovation here because I'm passionate about developing new solutions for the cement industry. So, and basically that contributing to pioneering the future. And I hope that many of you here also are passionate about that because we really need to push on to develop new solutions. I'm going to start with a very high-level outline on 3 ways to decarbonize cement. Then we're going to dig into the case study which we've chosen on development and implementation of the FUELFLEX Pyrolyzer in close collaboration with Mannok Cement. And then after that, the last part, we'll look a bit at what's next, so looking forward. There are 3 overall ways to decarbonize cement. I know I've simplified it compared to the 6 or 7 levers we had before. We have clinker substitution, we have clinker decarbonation, and efficiency improvements. So I think the clinker substitution is the most effective way of reducing CO2 emissions, and that's because we avoid the need to calcine limestone and therefore avoid the need to emit these CO2 emissions or spend a lot of energy and money on capturing and using this CO2 again. Of course, you could argue that the efficiency improvements over here are also really effective in reducing emissions. But there's a limited scope in these efficiency improvements. We've already gotten far with getting a high energy efficiency, both thermal energy and electrical energy. If we go to clinker substitution here, traditionally we'd substitute clinker using natural pozzolans or waste materials like fly ash or slag. But now, as we've heard, there's an increasing focus on using calcined clay, and so artificially producing calcined clay as a supplementary cementitious material. But we'll continue to need clinker for the foreseeable future, and that's why we need to do something to decarbonize the clinker. As we heard, fuel substitution is a really effective lever here. It's very cost effective and it also reduces the CO2 emissions. However, we only get about 1/3 of the CO2 emissions from the fuel and the 2/3 come from the process. So we need new technologies to capture the CO2, utilize it, purify it and store it. What I'll be digging into in my presentation is the fuel substitution part here. And this is where we've been working. And this is where the FUELFLEX Pyrolyzer at Mannok, the development of that fits in. It fits into the area of fuel substitution. I'll start with looking at what the FUELFLEX Pyrolyzer is and what pyrolysis is. We'll then look into how we developed and implemented the FUELFLEX Pyrolyzer. We'll then look at combining and refining the FUELFLEX Pyrolyzer and the technologies associated with this. I think this is an extremely important point. It's a bit of an overlooked point that to get the full benefit, you really need to work after you've developed the technology to refine it. And finally, we'll take a quick look at Mannok's next step ahead. But we also have Paul Monaghan here, who tomorrow will be presenting more broadly on Mannok Cement's overall way forward. If we look at pyrolysis, what that is, basically it's taking the fuel and then heating it up, breaking it down to form volatile components, and then the char. The bottom picture down here shows a piece of wood which is put into a laboratory furnace. When we then heat up this wood, initially the moisture evaporates from the wood, and then after that the volatile constituents are pushed off and it leaves the char behind. So this is basically what pyrolysis is, the first part of combustion, of most combustion processes. When we then add the oxygen, the volatile components and the char burn to form carbon dioxide and water, which releases the heat, which is what we need for the calcination. Let's now take a closer look at the FUELFLEX Pyrolyzer. Basically, the FUELFLEX Pyrolyzer is a technology which we've developed to substitute alternative fuels and reduce NOx emissions. The benefits we have is that with the FUELFLEX Pyrolyzer, we avoid a costly calciner extension, so building a big costly structure to give extended residence time for the fuel. And on top of that, we also avoid the costs of, for example, using ammonia to reduce NOx emissions. The way it works is that we take hot meal at about 800 degrees Celsius from the lowest preheater cyclone. We then take it through two dividing gates. The first one is conventionally divides the meal between the calciner and the kiln riser. With the second one, we can then divert it into the FUELFLEX Pyrolyzer, which is basically the blue unit you see up here. The meal flows first into what we call the U-lock, and this basically prevents the combustible gases from flowing backwards into the process. What we do here is we use a new pulsed aeration technique to get the meal to flow like water, so it basically behaves like a liquid. As we then pour the hot meal into the inlet leg, it runs out of the outlet leg, continuing over into the main pyrolyzer vessel here. Again, we have pulsed aeration down here where we fluidize the meal, so we have a vessel with fluidized hot meal. To that, then we introduce solid recovered fuel or the alternative fuel. We introduce that into the hot meal. As I showed before, it dries away the moisture, so the moisture goes upwards here. And after that, on heating up, it releases the volatile components, which also go upwards. The char goes down, following the yellow arrows here, together with the meal. The volatile components then come down with the red arrow there, meeting the meal, and then go into the kiln riser. And basically, this is the same position as we traditionally put in both the meal and the fuel. The difference now is simply that this unreactive fuel has become an extremely reactive fuel stream. This fuel then meets the nitrogen oxide coming from the kiln gas down here. Because it's so reactive, it then converts the nitrogen oxide to free nitrogen, and thereby we reduce the NOx. On going further up, it meets the tertiary air, and then it burns very quickly. Because it's also now so reactive, we can get away with a much smaller calciner design, so there's no need to extend the calciner. We can use calciners designed for fossil fuels to burn these alternative fuels. There's a detail to notice here. We have two drain gates at the bottom of the pyrolyzer. These are there and operate continuously during operation to drain out debris which comes in with alternative fuel. So often we have stones, metal pieces, and so coming in with the fuel. This sediments out and is drained out into the kiln, and then contributes to forming clinker. So this is overall the FUELFLEX Pyrolyzer. If we look at how we've developed it, it's been a process over many years. We submitted our first patent in 2017, developing the concept. We started with proof of concept there. Then in 2018, we worked with a prototype development specifically for Mannok. In 2020 and 2021, we worked with commissioning and design updates. This was in the COVID time, so gave us quite an extra challenge to deal with all these COVID challenges in starting that up. In 2022 and 2023, the focus was on optimizing. It was about optimizing the fuel feed and the overall process control. And right now, we're finalizing the installation of the second FUELFLEX Pyrolyzer at Continental Cement in Iowa in USA. Let's have a look now at how we did the proof of concept. So the proof of concept we did in our scale 1 to 2,000 pilot scale installation at our R&D facility in Dania. It's a hot continuous flow pilot where we started by feeding in wood pellets in 2017 and then got this to run, and in early 2018 we then fed refuse-derived fuel into this and got a proof of concept. Shortly after that, I visited Mannok Cement, and they were very happy about this. It fitted excellently with their plans. At that time, they were limited to about 50% substitution of coal in their calciner, not because they didn't have the fuel feed capacity for the alternative fuels. They had tried running with more than 80% alternative fuels in their calciner, but after several weeks or a month or so, the feed pipe to the kiln blocked. They blocked up the whole cyclone, so they had to pull back to about 50%. They needed more residence time or better combustion in their calciner, and this is where the FUELFLEX Pyrolyzer fitted in. Now we had to scale up by about 2,000 times from our hot pilot installation, and to do that with this new pulsed aeration technique, we built a pilot scale installation. You can see it over here in front of the big silo. This is the scale 1 to 2 pilot installation which we built. We then recirculated the meal over the silo and then used this to scale up and get the design details right for this pulsed aeration. On the picture over here, you see what a pulsed aeration meal looks like. You see the characteristic fractures in the meal here caused by the pulses of air going into the meal. We then, in 2019, we did most of the installation work at Mannok. We actually started with the first parts in late 2018 and then concluded the work in 2020. What you'll see over here is the main pyrolyzer vessel, which fits nicely into the preheater. Then out here on the right, you actually see where the FUELFLEX Pyrolyzer fits into the preheater, and you can also see the space which is freed up in front of the kiln. This was where the alternative was to put in a big, costly calciner in front of the preheater. As I mentioned, during COVID in 2020, November 2020, we then started up the FUELFLEX Pyrolyzer. It actually started up extremely well. We had success with our pulsed aeration of the hot meal. It flowed nicely through the process. When you put the fuel in, it pyrolyzed well as it should, and we also got the NOx reduction. So we were actually extremely happy. But then after about 2 weeks, we really got into trouble, because now the whole pyrolyzer blocked up with buildups. This was the debris I talked about before. It started sedimenting out in the process. Here you can see wires and stones and things like this sedimenting out in the process. And we had this extremely corrosive environment with sulfur and chlorine and so at 800 degrees. And then when you stop the aeration, if any of you have had blocked cyclones and leave it blocked for a while, you'll know that everything consolidates to one big lump, which is difficult to take out. So we had quite a battle with that, and we needed to reconsider the whole design of our aeration system for this pulsed aeration and the bottom of the pyrolyzer. So basically, we rebuilt the whole bottom part of the pyrolyzer, and in about 8-9 months later, we were ready with the new installation over here. You can see the redesigned bottom of the pyrolyzer. Now we had actually put a second generation and a third generation aeration system in to be sure that we'd get it right. Just below that, you see the 2 drain gates, and then you see our commissioning team starting it up again in 2021. Over here to the right, you see the control panel, which controls the process. It was now we could operate it well, and it got the benefits which we were looking for NOx reduction. Over here, I put in as the baseline. That was basically before we installed the FUELFLEX Pyrolyzer. You have about 50% coal and 50% alternative fuel in the calciner. The second line here is the situation where you put about 80% alternative fuels fired directly in the calciner. And the third column here, we have 10 tons an hour of solid recovered fuel going into the FUELFLEX Pyrolyzer, and the rest going into the calciner. Here we have 90% substitution. What you'll notice here is in the baseline, they're using about 200 liters of ammonia water per hour to comply with the 500 milligram NOx limit. It was actually quite similar when firing the alternative fuel directly to the calciner. A little bit less, but still close to 200 liters per hour of ammonia water to meet the NOx limit. Now, when putting in the FUELFLEX Pyrolyzer, they didn't need to use any ammonia water at all and were operating at a much lower NOx level. So clearly demonstrating how important it is to get the fuel to be very reactive, to be able to reduce the NOx. This is then what the FUELFLEX Pyrolyzer looks like. We have the U-lock here preventing the gas from going backwards through the process, and we have the main pyrolyzer vessel here. We were happy to have it substituting more than 80% of the fuel, and we had a visit by Mannok Cement, who actually also were very happy with what they saw. This fitted very well with their plans to replace 55% of all the fuel on their plant by alternative fuels. So they quickly opted in for a new FUELFLEX Pyrolyzer, and this is the one where we're finalizing the installation now during their current shutdown, and then during the coming months we're going to start this up. This is really exciting because now we're going to be able to test different fuels. They have quite different fuels from what we have at Mannok, so we're going to broaden our experience with this. The process is also different. They've got a preheater stage less, and chemistry is different at all plants. So we really look forward to broadening our experience base on this. As I mentioned, we had reached 80 to 90% substitution at Mannok, but then the targets were lifted now. Now they wanted to get rid of all of the coal in the calciner. To do this, we needed to look at what were the bottlenecks. We had the alternative fuel dosing, which couldn't quite substitute all of the fuel. So what we did there was to debottleneck the mechanical feed system and to boost the Vista feeders feeding the alternative fuel. In addition to that, we then looked at the coal dosing and the overall process control. If we look at the coal dosing, this was, when we had increased the alternative fuel capacity up to 100%, we still needed the coal because, as with most alternative fuels, pipes block once in a while, and you need to compensate for the missing alternative fuels. So they needed to keep the coal on. At the beginning of last year, Mannok installed a FeedFlex upgrade to the coal feeder, which means now the turn-down ratio for the coal feeder changed from 1 to 10 to 1 to 100, which means now they could operate with 99% alternative fuel in the calciner and then have the 1% coal as standby coal, but they still didn't lose the ability to ramp up the coal quickly to replace these alternative fuels. So this was really good, and now it meant that they could run with 99% substitution in the calciner and minimal coal. The next challenge was now to ensure that the operators did this whenever possible to minimize the coal to an absolute minimum. And to do this, then they upgraded their PXP process control system, and with this we were able to maintain the coal firing at an absolute minimum and still control the process very well. This is actually illustrated quite well by this chart over here, where the black lines are the coal firing, the blue lines are the alternative fuel firing directly to the calciner, and the green lines is the alternative fuel going to the FUELFLEX Pyrolyzer. The red line is then the total alternative fuel going to the calciner. If we start over here, we can see that they're firing about half of the fuel in the calciner being alternative fuel and the other half being coal, both being fired directly to the calciner. We then see, and at that point, you see that when the alternative fuel blocks, the coal takes over, so firing about 13 to 15 tons per hour of coal in the calciner. At this point over here, we then put on the FUELFLEX Pyrolyzer, putting in 10 tons per hour of alternative fuel into the FUELFLEX Pyrolyzer, and we then see the coal going right down to 0.2 tons per hour, so minimal coal in the calciner. It remains down here, and the process is controlled by the alternative fuel being admitted to the calciner. Every time the fuel might fail, the coal kicks in and otherwise goes down to a minimal. What you'll notice at the end here is that then the coal takes over. And this is because the alternative fuel calorific value has been dropping over time. So you need more and more alternative fuel, and in the end there's no more capacity in the feeders, so the coal feeders take over. But this has been extremely effective to really minimize the coal consumption at Mannok, so showing how it's important to look at the process as a whole. Now, having reached this target in the calciner, Mannok's taking the next steps to get rid of the coal in the main burner. So right now, they're installing a fuel handling system for the main burner, a satellite burner to supplement the existing DuoFlex burner, and next year we'll be installing a JetFlex burner to go all the way. That was the case which we had on fuel substitution. We also are working on calcined clay, and right now we're actually also implementing a few calcined clay projects. These also come from our beautiful R&D center at Dania. We're taking the technology which we have made proof of concept for at Dania and installing that at 2 plants. I'll get back to that. You'll notice here we have the silo, which I mentioned before, which we used for the proof of, or for the scale-up of the FUELFLEX Pyrolyzer. And if we go within this hall here, you'll notice that we have the same pilot installation which we use for the proof of concept for the FUELFLEX Pyrolyzer, which we also use for the proof of concept for the calcined clay, particularly our color control process for the calcined clay. We're installing 2 installations, 2 flash calciner installations right now. One in Zeuilly in France, which has a capacity of 525 tons per day, and the second plant in Accra in Ghana with a capacity of 1,200 tons per day. Both of these plants will come into operation in the middle of this year, and again we look forward to getting this installation in operation and getting the first full-scale experience. We have 3 standard sizes of our calcined clay systems, 500, 850, and 1,200 ton per day. You'll notice the slight difference in capacity. This is because it depends on the moisture content and other process conditions as well. A benefit of having these standard capacities is that we can quite effectively and quickly implement new projects for calcined clay. The last part I have is then looking a bit forward on what else we're doing, what the new technologies which we're going to implement in the future will be. We don't know exactly, but we have many places where we have activities. We have some collaborative research projects. You'll see here we have our CO2 valorize project, which looks at valorizing CO2. So either using the CO2 to make a valuable SCM product, or simply binding it in by mineralization, which reduces the need for purification and the need to use a lot of energy and money to purify the CO2 to be able to deal with it in other ways. We have our eco-clay project, which looks at electrification of clay calcination. We then have our new cement, which looks into oxyfuel, really promising for if we have to do all the carbon capture and storage, we need to do some oxyfuel as well. We have our detox, which is basically digital modeling of concrete strength development. So again, to reduce the amount of clinker which we need to build. Concrete recycling fits into this sustainability, so the circularity aspect. And then finally, we have our Tomorrow FUELFLEX project, which looks at getting more out of our FUELFLEX design, but also using some of the principles and experience which we have for other applications. So I think this is quite a good illustration of where we're going in the future after implementing these projects. So to summarize, I went through 3 ways to decarbonize cement: clinker substitution, clinker decarbonation, and energy efficiency or efficiency improvements. We then zoomed in on the FUELFLEX Pyrolyzer, the bright spot in the preheater, which you see over here, and our journey in developing this. We then looked at the next technology going from our pilot demo at Dania to industrial installation. And then finally, we looked at a summary of the collaborative projects which are shaping the future. So I think this is really exciting, and we look forward to these 2.5 days, and hopefully we'll discuss a lot on how to create a more sustainable future. And you're very welcome to visit our booth, where we have a lot of good colleagues there, both if you have technical questions and need technical solutions, or want to understand more about our organization and what's going on right now. So thank you, and you're all welcome to visit us.
It is now time for our joint Q&A session, so I'd please like to welcome Paul and Antonio back to the stage. And remember, you can submit questions via Slido, so we'll try that again, see how that goes this time. But I will have some colleagues in the audience going around with microphones as well when we get around to taking questions from the audience. Okay, well, thank you, gentlemen, for all of your excellent presentations and getting EnviroTech off to a fantastic start. Now, I'm going to start with you, Paul, in the theme of optimism that you set us off with. By your estimates, is the cement industry on track to reach net zero by 2050? And if not, what do we need to do?